You'll note near the end of the agenda that is provided to you, there's an opportunity to talk about a number of topics and follow up on some of the topics we've had, and also to provide you with some additional input in some areas. The one I'm going to, and we'll digress to this discussion, and then we'll return to the regular agenda afterwards.
I'm sorry, Phil.
Oh, you're going to steal that, all right? Hey, by the way, you're the only one that does things on time. The rest of this crowd doesn't know how to do that. The subject we're going to go talk about initially here, before we return to the regular order of agenda, is in the area of common cause failures. You may recall that we've brought this up in a number of different contexts, but in particular, in the case of what occurred at Davis-Besse in its 1985 event. And we've extracted part of that event here for purposes of demonstrating how the newer concepts of risk-informed capabilities might be applied to get a better answer. Now let me remind you what the cause, I'll call it the causes here, but let me just remind you what occurred. We've picked this part where the operator has an error of commission. He pushed the incorrect manual trip switches. One on each division is pointed out here. Low steam generator pressure rather than low steam generator level. And the result then was for demand for the auxiliary feed water pumps to start and a containment isolation valves to close. That's not what he wanted, but that's what he got, because that's what he asked for. There was a design failure. The logic of the steam and feed water rupture control system failed to recognize that the operator had really made a nonsensical demand to realign the steam supplies to the auxiliary feed water pump turbines, basically to realign them to steam generators that the other part of the logic of the steam and feed water rupture control system just recognized had failed. So that's a nonsensical request. There are also design and testing failures. Both of the auxiliary feed water pumps failed to trip, or rather tripped on overspeed due to excessive water in the steam lines. The reason that's a design and testing failure, okay, one, the steam lines were excessively long with no consideration of the condensation that was going to go on when you go through these alternative paths. Number two, the acceptance testing, now this is I'll call that the startup testing, the acceptance testing that was done, was gun-decked. Does that term translate in here? Okay, gun-decked, that is, they set the testing up in such a way as to succeed by pre-warming the lines, so that the phenomena that led to the overspeed trip wouldn't have occurred. So that here's and I consider acceptance testing as part of design confirmation in the plant, all right? So now we've basically challenged the design confirmation by setting ourselves up to succeed, even though it doesn't represent the way the system really works. And lastly, we had design, maintenance, and testing failures all combined, with primarily design being the primary item. And this is that the containment isolation valves failed to open on demand. There was differential pressure across the valve due to steam generator pressure on one side, essentially no pressure on the other, and the torque switches that are there to protect the motor were not set high enough to deal with the differential pressure. And I call it a design problem because it wasn't acknowledged or recognized in the design direction that you need to consider that as part of how you set up the valve. So we have this cascading issue, started by the operator, failures in design of the logic circuit, failures in design of the auxiliary feed water pump turbine system, and failures in the design of setting up the containment isolation MOVs. This isn't very clear, okay? But what you're looking at are the 10 buttons, the 10 trip switches that are on the panel that the operator, this is behind the panel now that the operator, control panel the operator is using. And this is what he was trying to do was to hit the lower two switches. left, right, 2 divisions, 2 trains, okay? And he wanted to hit where it says steam generator low level. There's 2 buttons, 1 for each side. What he hit were the upper ones, steam generator low pressure. Now, we can debate all day why he did this, but he did. And if you could read the labels a little bit better, both of the indicator, the labels that are on there start out with the words steam generator low, okay, on both locations. They continue on to say the right thing, but steam generator low is the first thing you can see. And so this is what he did incorrectly, was subsequently corrected by his supervisor, but it was too late, as I discussed earlier. This is a sealed-in process. Once it happens, it goes to completion. And then we run into the other common mode failures that basically couldn't be recovered by just resetting the system. I remind you that what we're looking at here is at 2 different levels. First, the auxiliary feed water pump trip. Both of those auxiliary feed water pumps tripped on overspeed. They were obtaining their steam from the opposite steam generator of what they're normally receiving it from. It was the long line, lots of condensation in the line. This is hundreds of feet, by the way. This isn't, schematically it looks like, oh, it's all the same, okay? In the plant, the alternative path from number 2 steam generator to number 1 auxiliary feed water pump, as an example, is a couple hundred feet of pipe. And the steam traps do nothing for you, those of you who have that practical experience. Steam traps just sit there and watch this all happen because there's no way to grab that amount of water. So the design issues, this is a terrible design that we're trying to live with, and then we never really understood it via the acceptance test program, which I mentioned to you earlier. The other side of this coin is the auxiliary feed water system on the fluid side going to the steam generator. This is in both of these, both the one previously and this schematic, you notice all this crossover stuff. The reason all these crossovers exist is because of single failure considerations. So what we've done is we've built in some problems by trying to solve other problems. And that's a larger discussion, okay? But the valves in this case are the ones that are marked with the pink or red or whatever color that is, X's across them. Those valves closed and then would not reopen. So the question I posed to the guys who are working on this area of risk-informed techniques to complement what were historical approaches to the design of the system is, what if contemporary risk-informed techniques have been applied to the Davis-Besse design process rather than solely deterministic and expert elicitation, which was the way the design was done originally. So let's bring it, you can think of it this way, let's bring the Davis-Besse design of 1985 forward into the contemporary world, and let's look at it a bit. And then the other part of the question is, with the event sequence and quantitative risk analysis, the newer aspect of this, have identified the design vulnerabilities. I'm not after absolute numbers of any of this discussion. What I'm interested in are design vulnerabilities, things I should pay attention to, and would I have led myself to mitigate via design changes to preclude the consequences of the error of commission. Again, the operator started this particular sequence this time. Would I recognized enough to mitigate via design change? We're not going to discuss exactly how you change that design. That's a longer conversation. But would I've identified it so that I knew I needed to go do something in the engineering design process to fix this problem? So I'm going to leave it. Which one of you guys is going to lead this conversation? Jim?
Yes.
All right. I'm going to leave it with you at this point, all right? Who's got the magic switch? See, Kamal took off with it, right?
Oh, I got it.
Ah, there it is. Okay.
So a couple of points before I start through this discussion. I guess Well, and I'll come back, or our group will come back around to this as we get near the end of the discussion. But the way we look at this approach, which I haven't covered with you yet, I'll be going through this in a bit more detail in some slides later on, is it's what we feel is an updated and more comprehensive approach or process that can be applied that gives you a much higher likelihood of success in covering all your bases. That process relies on taking advantage of some updated and refined tools like the PRA, but not only the PRA. And when you apply those tools through this updated process, you get a lot of very useful information, but it's only helpful in the grand scheme of things if you're comprehensive in how you execute what you learned from that process. The other point I guess I'd like to make there too is throughout this whole approach, it's really sort of it takes a village kind of an issue that requires a lot of engagement and involvement from the whole organization. Sometimes I think folks go away with the concept of if you're going to use a risk-informed or risk-based approach, if you lock 5 PRA analysts in a closet for a year and they generate a report, that'll tell you everything you ever need to know, and you'll never have a problem with your plant when you design, construct, and operate it. So that's just not the case. We're going to try and talk through some of those topics as we go through this. I'll invite some folks, both Bob Youngblood up in front and some folks in the audience who've got more specific and recent experience either with operating units or in developing this approach for the newer units to move forward. So Bob, do you want to say a few words about this slide since it's yours?
Well, really, it's if anybody here owns that slide, it's Roger, because it came from the ASME Presidential Task Force report. I did use it, and I've highlighted the part about common cause failures because the chart contrasts the old way of thinking about common cause with the new way. And the old way was if we impose enough process on components, we can make things like that go away. Whereas in PRA, every PRA person would instinctively and by standard guidance choose to model CCF on of the ones that occurred in that event. So we would clearly know about them. I think another point to make right off is that one of the modern things that you're supposed to have, even before we get here, I think I mentioned yesterday that one of the things that happened as a result of WASH 1400 was that people began to think about what reliability that they would want out of auxiliary feed water specifically, given that transients and small breaks were so important. And so one of the things that began to happen in the early 80s was that there's people articulated expectations for that system that had not previously been articulated. So sort of statement zero, if we're trying to roll that system forward and think about it from today's perspective, any reasonable evaluation of it one reason for it is it's got 2 trains, and the other reason is CCF, and I think we'll be going more into detail as we go along.
So this is a kind of a process slide I added. I may talk about it a little bit more later on. It's intended to be the general progression of typical technology development and design stages and how those marry up with how you go about identifying the upset conditions or the events or what we're calling licensing basis events that you ultimately need to deal with as you get to the back end or the more detailed part of the design and the actual licensing process. So you start off on the left, again, depending on the technology you're pursuing or the level of maturity of that technology, you either start with some older designs or you start with the back of a napkin and you start working through based on the design you have in mind, what you think the most likely challenges or events might be. So as depicted in the bottom in that pre-conceptual phase, you look at the initial concept. This one was actually a chart that came from a General Atomics approach from back in the mid-'80s. So they had some prior gas reactor experience. They had some initial PRA information. But it's largely an initial set of design discussions and expert elicitation, just like the old days with LWR. So that's where you start. As that process matures, and I won't go through every step here, but as that process matures and you move into a more conceptual design stage, you get more insights about initiating events, the design keeps coming along. You do failure modes and effects analysis for individual SSCs. Your PRA matures a little bit more. You start to run the first more updated versions of that. The design requirements come along a little bit further. The same experts, plus maybe a few more, come along and provide some thoughts and insights. So the point here is this is a kind of an evolving process that gets a lot of inputs from a lot of places. And as you move from the left to the right on this chart, you always want to use the most useful and updated tools. And in this case, we reflect the fact that the PRA is further refined along the way. So you loop through the PRA everywhere along the process, so that when you come to the end and the design is relatively mature or is mature, and you're ready to finalize its detail and start building it, you do one more pass through with the experts to make sure you haven't missed anything. And then when you get to that place, you can be pretty confident that you've considered and have identified all of the event sequences that you would need to think about or consider. So again, an event sequence is a bit different from an initiating event. It's the whole soup to nuts from what was the initiator or the upset that caused a problem with the plant, and then where does that go through the plant's capabilities and what comes out the other end, and once the plant is stable or shut down or at the end of the event sequence, where are you? So this approach, again, provides a lot of inputs. It's very iterative, and the intention at the end is you have a pretty good understanding or a pretty good salad bar of all of the event sequences that you need to deal with.
So what if contemporary risk-informed techniques had been applied during the design process rather than solely deterministic? First of all, the little bullet in red is saying that a major purpose of risk analysis, of logic modeling as we do it, is to identify conditions that effectively reduce redundancy in risk-significant ways, like these CCFs do. So in a way, the whole point of risk analysis of Gen 2 plants is exactly to try to nail this kind of stuff. So the next bullet is a kind of a direct quote, nearly direct quote from one of the early PRA standards, which says, model CCF for MOVs, pumps, and so on. Just do it. And by just do it, they will mean typically put an event into your model that says CCF, so that instead of looking like two things have to happen, it's really one thing. It's the one common cause that has to happen that fails the two trains. And by the way, just to begin to set a numerical scale, early common cause thinking, which actually preceded WASH 1400, realized that empirically the failure probability of particular components, some fraction of that probability tended to be common cause. In the early days, people said maybe it's 10%. Nowadays, it might be 2 or 3%. But so if a component is unreliable to begin with, the belief will be that it'll have a high common cause failure probability as well. So just reading, I guess if we wanted to really do this, we could pull up the train diagram, the diagram Phil showed earlier, and put numbers on it. Maybe that's too far for right now. But in addition to modeling CCF, you're supposed to perform engineering analysis of support systems. This is all in the CCF discussion of that old standard. And I put there steam supply lines. Okay, that's kind of counts as a support here. You should be looking at that as part of your CCF effort. Include the support systems required, actuation logic specifically called out, the buttons. Component motive power, steam. I guess it's so obvious it's gone without saying that you don't have diversity in a system with 2 steam turbine-driven pumps, okay? Now, it hasn't gone without saying. I won't bother to make a big deal out of it. So all of that stuff would be stressed in any standard risk analysis, just from a combination of the diagram and engineering analysis of the steam lines. I think I said this yesterday, but I'll stress it again. You know, the chart I showed earlier from the ASME report has deterministic kind of implicitly versus PRA. And in reality, PRA is always on top of a large body of engineering analysis. So everything that determinists did that makes any sense, we use in the PRA. And that's related to this taking a village comment, which is going to recur as we go along. Then finally, one of the parts of it that seem a little trickier to me than the stuff above that on the slide is that the, some people could look at the diagram, the MOVs that closed and couldn't be opened were open before the event, and they'd say, well, okay, they're going to be open. I don't have to worry about opening them. And yet a more sophisticated hazard analysis should maybe turn up the fact that, they might not be open. Yeah. 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 I don't know if everybody could hear that. Roger is pointing out that that block valves were closed at TMI in a kind of a logically similar position. I think distinct from these, but not that distinct. They were closed. And then finally, yeah, PRA guidance says to model failure of an open component to remain open. In this case, of course, they hadn't spuriously transferred closed. In retrospect, somebody knew they were closed. Now, are we alternating here?
I would like, you can cover this one as well if you'd like.
Okay. This is back to the taking a village comment, and we're grateful to, it's actually my slide, but Amir made the connection with the discussion that we're trying to have. This was part of yesterday's discussion of 5069, an application of risk analysis to component classification. We're not really talking about component classification here today, but what this diagram has on it that's germane and that's common to numerous modern risk analysis application approaches is that it's showing you how to think about, on the right it is the answer of how you should be thinking about these components, but beginning on the left is a risk-informed understanding of what those components are doing in the plant. And so you think about the risk model, you think about defense in depth, I'm working down into the right here, you do sensitivity studies, and then you get to the village part, where it's integrated decision-making panel. And in that dialogue, issues are meant to be raised that maybe the PRA guys didn't think of, or that the PRA guys did think of and the other people had not. So this is the village part that Jim mentioned earlier. And that's the group that has the final say in categorization. And a group like that, in a modern way of approaching this, the possible problems with this system, you would hope that that would flush out, there might be residual issues left unflushed by that panel, but shouldn't be many.
One quick note there for those who might not be familiar with the lingo. 5069 is a part of the NRC regulation. It's called the maintenance rule. It's been around. No.
5065 is the maintenance rule.
5065 is the maintenance rule.
You're 4 rules off.
5069 is applying risk to the classification process. So it's been around for a while and is being implemented in various stages and to varying degrees in the operating fleet. So just stepping through the, we went through the 4, or Phil went through the 4 beans that were associated with the Davis-Bessey event. So just a few notes about each of those. So this is the topic of the common cause failure, where you've got a sort of a difficult to understand control board setup where an operator made a mistake, pushed the wrong buttons. A couple of observations I'd make here. So we'd expect that this event sequence, or the event sequence that required you to take this action, would have been included in the PRA and the outputs of the process that Bob just described. I'll tell you that on this human-machine interface topic, based on some past involvement I had in the certification of GE's ESBWR design, when we got within a few years of the finish line on that effort and the control room design was being finalized, the human factors and human-machine interface team turned out to be the largest team in the whole engineering organization in pulling that together. It's partly because there are a lot of very stringent requirements. You want to make sure you do the right thing. It's sort of a combination of engineering inputs, a little bit of art, a lot of psychology of operators, so it takes a lot of very specialized skills to do that evaluation. And honestly, the NRC branch chief, who's now retired, so I can say this, was running amok a little bit on his side of the table, so it was a very, very big effort. But what I can tell you is at the end of all of that evaluation and related pain and suffering, you come out with a very, very, very robust control room design that has the human factor element very firmly in place and in front. So it makes this kind of an arrangement very unlikely, and this kind of an error less likely to occur. Doesn't get you away from the blue screen of death that you mentioned earlier. It's not a different topic, but again, there have been leaps and bounds improvements over this whole area since the days of Davis-Besse and some of the older control room designs that George covered a little bit earlier. Bob, I don't know if you want to say anything more about the common cause part of this, but
Only to reiterate that when somebody like me refers to a common cause, we mean you were supposed to have some level of redundancy and something happened that compromised it. And in this case, it was one guy hitting two switches that were both wrong. That's the one cause in this piece of it.
So moving on to the next item, this is the one where, as Phil mentioned, there's a very long steam line run. It tends to collect condensation. The downside of that is when you start a a steam-driven turbine like that, the moisture causes it to overspeed and trip, and that's what occurred in this case. So, again, I think the sequences that this system would be required to respond to would be pretty clearly identified in the PRA. They were probably pretty clearly identified even back in the Davis-Besse days. So this is more of an issue of not carrying forward what you know from that sequence where the system's going to be required to operate, and making sure that your acceptance testing, maintenance operations, and regular surveillance testing programs and processes carry those engineering design assumptions forward to be sure that you're confirming that the system will actually work when it's called upon. Again, I know a couple of times through the years, this isn't common only to Davis-Besse. I know a couple of times through the years the NRC has put a lot of focus on how individual licensees do their surveillance tests, because in some cases, either inadvertently or on purpose, they tend to preload the test, I'll call it, I guess, so it's more likely to pass. Again, sometimes that's done without recognizing it's happening, and sometimes not. And so again, that plays a part in this topic. Anything else you want to add on that one, Bob?
Well, Phil, is your microphone still on?
Now it is.
Oh, okay.
And I apologize to the group for sharing my duties outside. Okay.
Okay, I just want you. I only hear the word gun decking in these workshops, and Jim didn't say it, but this is the right figure for it, right? This is where they were warming up the steam lines before testing them on at least the crossover lines.
That's correct. Yeah.
And so if, you know, if I were you, I'd be taking away the term gun decking. I think it's a really, really fun term. And that's why the problem wouldn't have shown up in data that people like my colleagues would be analyzing at the INL for, you know, failure probability data.
So again, this is back to the takes a village kind of an idea. You'd have to have folks knowledgeable in plant operations and maintenance to realize that, as you said, a really long steam line run tends to collect condensation no matter whether it's got traps in it or not. And you also have to be, you know, sensitive to doing the right surveillance testing. Or the,
well, there are really, really two issues on here. One is the fact that the main point of this slide is shown by the little red X's, because pushing one of those wrong buttons told the system that steam generator 1 was faulted and shouldn't be fed. Pushing the other button told the system that steam generator 2 was faulted and shouldn't be fed. So 2 out of 2 shouldn't be fed, and the way that's accomplished is to close those red X'd valves to make sure that flow doesn't go from the aux feed to those steam generators. And you might think that that would be easy to reverse, but in the event it was not, because to the left of those valves you have low pressure when they're closed, and to the right you have high pressure. So that high pressure kind of mashes on the valve and makes it, that's work you have to do to get it to open again. So that's, you could describe that situation in various ways. The PRA people, even without, well, we would have modeled failure, a failure event corresponding to transfer closed spuriously, and then we should have asked about then common cause failure to open. The other thing, I don't know if it's on this slide or some other, I tried to make it sound nonsensical what those 2 buttons tell the system. And at some point, someone needed to ask whether it makes any sense for that illogical instruction to be given.
Yeah, I guess the other point to make here too, again, back to the takes a village idea, is plant licensees are required to have a motor-operated valve program that assures all their safety-related valves are set up correctly, maintained correctly, and will work when called upon. So the other point here is that this event sequence that occurred at Davis-Besse would have been identified through the PRA and other related tools, and that would have provided a set of conditions or the opportunity to identify the set of conditions that should have been incorporated into the plant's motor-operated valve program for these 2 valves, and that would have helped to assure that those torque switches were set in a way that would allow them to respond in this event. So,
comment over here.
certainly.
So the cross-connect in the early emergency core cooling systems, and I think the aux feed water systems, there were no cross-connects because we only had to consider a single failure. And then somebody said, well, what if the single failure in one line and you have another single failure in the other line? It wasn't a common mode failure, it was coincident single failures. That led to the addition of the cross connects.
Yeah, and the other part of that, Roger, was the so-called concept of the smart brake. Now, it's not very, I don't know why the term smart brake, but that was the terminology that was used, that combined with the single failure, that we had a break occur in an area that compromised steam, like a high-pressure line break that compromised the other train.
Yeah, if it occurred near where the injection was going in the case of ECCS.
That's correct. Okay.
And an observation there, one I'd be interested in feedback on is as you consider these expert judgment-based breaks, or apply the single failure criterion, and you find the need for this cross-connect to address it, now you're incorporating more components and more places where other failures can occur. So now you've got more active components to deal with that particular break. So it's, you know, it's not always clear unless you apply updated tools whether you've made any progress in fixing the problem. Right. Right. Yeah, exactly.
Jim,
I note that this particular event and these particular two valves and this particular sequence that we're talking about was the cause and led to the motor operated valve program that Jim just described as the basis to solve it. Okay. So obviously we wouldn't have known it at this time, but the question was bringing it into the contemporary world. Would we have picked up on it? Let me just ask one other question. By the way, I invite questions. This type of discussion is invite questions from the group if you want to look at, or ask a question differently or do it differently. Let me come back just to one item, okay, that leaves me uncomfortable just because I don't understand how I might find it. And this is what I call the illogic in the steam and feed water rupture control system. You mentioned it a little bit, Bob. Basically, the system is two-sided and one side doesn't know what the other side's doing. And when the operator told it to both sides by pushing the two buttons, that both steam generators were faulted, but the logic is single-sided in that it says, well, okay, switch your steam supplies then. So the illogic of that action, okay, and no caution light that comes up like somebody used earlier that says, are you sure this is what you want to do? Would that illogic, how would we find that illogic? Because it's obvious after the fact, but before the fact, it may not have been very obvious.
in modern times when people are trying to analyze digital systems for performance, they try to consider as many possible permutations of the inputs as they can, just in case some screwball thing happens when you put in an odd combination that you hadn't meant to put in of data. And so when you asked the question the other day, you know, that process came immediately to mind. I can't imagine what was going on in discussions of that design, except maybe somebody, probably a manager, said, oh, that'll never happen.
Yeah, well, how are we going to have two steam generators faulted at the same time? How would that ever have occurred? Okay, and the answer is it didn't occur, but the operator told the system it did.
Yeah.
Okay. And so I find that one difficult to find. I appreciate that there's no simple answer to the question. But these items that have just been discussed and described point out a number of issues on how important it is that the risk environment, I'll call it the risk environment, the risk approaches, be complemented by some smart engineering processes in the expert process, elicitation process, to find these kinds of issues. Because after the fact, it becomes obvious. Before the fact, not particularly obvious, because we had to combine some things, some actions of people with regards to gun decking. I use that word, that's a Navy term, gun decking, the I'll call it, it wasn't falsification in the sense it wasn't intentional, but it happened, okay? And because it wasn't intentional in the sense that they didn't realize they were compromising the test results, okay? It was intentional to do it, but it wasn't, they weren't trying to compromise the test results according to the folks that had done it. This is an interesting set of questions. It leads to a lot of questions for your future activities as you try to look at designs. It clearly underlines the need to stay away from the complexity of systems of this nature. This is typical, as Roger was pointing out, this is typical of the Generation 2 light water reactors. This kind of configuration repeats itself throughout the reactors. It's been a battle to make sure that we have the appropriate level of understanding of how the systems may react. As we go forward with innovative and advanced designs, we need to find ways to stay away from the complexities of both the fluid systems and the control and systems to, one, better assure success, and number two, don't challenge the operator trying to figure out what's really going on like this, okay? And in this case, the operator figured out what was going, shift supervisor figured out what was going on solely by the fact he looked at the indication lights of trip on the panel. Not because he could figure out what the plant had done, but he looked at the indicating lights. If he hadn't had those indicating lights, hadn't gone by behind the panel, looked at them, he would have never recognized he had the problem for quite a bit. Are there questions from the group?
Greg Krieger, Exelon. As former director of risk management for a lot of units for a lot of years, a couple things I want to say about common cause. You know, in a way, it's being used as a demonizer for digital, for safety-related equipment these days. You know, common cause in software is being used in such a way, I think, to say we don't want to go there, when in fact it's being used, you know, on the non-safety related side all over the place. Common cause also has to be realistic. If it's done conservatively, it masks a lot of other things in the PRA. And what might be important becomes unimportant, because it might be the support system that supports the diesels, not the common cause of the diesels that's important. So it's really critical to look at common cause in a fair way and not to somehow conservatively drive it in one direction, as you well know. And the last thing I just want to say, and I think it came down to accident signals. Design basis has a negative connotation in many ways for other events. So the more we tend to focus on design basis LOCA, the more we dug ourselves into a hole that caused difficulty for losses of offsite power and other type events in current reactors. You know, we isolate containment almost immediately in BWRs. What does that do? That takes away all our non-safety related equipment that is normally pumping water into the reactor, takes it away as if it's a loss of offsite power. That's a negative consequence. The probability of having a LOCA signal, as you also well know, in a BWR, is probably 3 to 4 decades higher than the probability of having a LOCA itself. The machine doesn't care whether it's a real event. It cares about the signal. The signal is what's important, and it's going to react to that signal. And so as a designer, you really have to look at design basis events and what parameters are being measured, and then what negative or unintended consequences can come from those parameters. That's why I'm a big believer, you know, and George talked about this yesterday, is I want the operator in there. I want the operator assessing the condition of everything. I don't want the machine just reacting on one, you know, a level indication and doing something automatically necessarily, unless it's needed in a fraction of a second. I think you need operations crew. You need a broader view of the world in order to respond to events, and not necessarily try to design everything, you know, automatically, because there are negative consequences.
Vince Pekanskas, Entergy. Very interesting discussion, but what it causes me to think about is that in a PRA, we generally model the success or failure of an action. We don't look at the potential for recovery, okay? Or we don't model the recovery generally. It's lost, right? You do model recovery. Okay, I haven't seen that, so forgive my ignorance, but yeah, you don't get a lot of credit for recovery. Part of this was a latent, and I would say, I'm in engineering, I would say it's a latent design error that we didn't properly set up the valves, and you couldn't possibly know that in doing the risk assessment, right? So one of the things I've started looking at is there's at MIT, there's a Dr. Nancy Levison that has a what she calls system theoretic process analysis. And I think the one key thing that I've taken from that is that she adds modeling of untimely operator actions. Okay, not that they completed the wrong action, but if I look at a boiler and I say, okay, I do an emergency depressurization. If I do it too early in a sequence, it's almost catastrophic. If I do it too late in a sequence, it's catastrophic. And those types of concepts, I think we need to drive into the design of the next generation of plants.
Yeah, thank you for that. I'm somewhat familiar with that work, and it's, believe she calls it unsafe control actions. And so she has a view of life that actually most accidents can be thought of in terms of unsafe control actions. And to go back to Greg's comment for just a minute, when I entered the field, the first thing I looked at was a risk analysis that postulated common cause failure of the batteries. And it was a 2-division plant, and you can guess that that dominated. And the effect of that was exactly what Greg said. It masked almost everything else. And another thing that's sort of gone maybe without enough emphasis is when we put events, common cause events, into a model, we're not saying exactly, well, the torque switch is going to be reset and here's the probability of that. We're simply allowing for things that we don't know but have empirically learned to not ignore in our risk model calculations. A risk model of that system with no accounting for common cause would underpredict the real system level failure frequency. But that said, the old numbers started out around 10% per CCF, and over time they should, and I believe do, go down. So, and then finally, we were trying, and in all this take a village business, we were trying to stress the collaboration between the risk guy in the back office and the systems people, the plant systems people that would actually be more alert to certain possibilities of misalignment. And that's what we meant in part by healthy discussion on this slide. The village part where somebody might have actually thought about somebody pushing 2 buttons. And so I'm trying to say on this slide that we would have spotted a lot of that stuff a priori. I can't swear that we would have spotted everything. And one comment I'd like to add is that if I used to read a lot of events in the early 80s, and based on all that reading, no one of these failures really astounds me. Stuff happens out there. The collection of all of it surprises me, and surprise to me, you feel surprised when something happens that's not in your model of the world. And so the constellation of these things surprises me. It's not really in my model of the world. And so to me it says there's higher order coupling here. And it's my PRA guy way of pointing to Phil's overarching point about management. You want to add to that? You dare to add to that? Okay.
Question. I have a question.
Oh.
Kind of a burning question since we talked about this yesterday. What is the core damage frequency of this chain of events, the Davis Bessie 1985? Has anybody looked at? I'm sure somebody has, but what is, if you look at that event tree, what's the frequency per reactor year of that happening?
The way we would normally quote that is that we would say, given that the things happen, given the things that happened, how much else had to go wrong?
Right.
And actually, well, I'm aware of at least one number for that that's pretty high. I think many people consider it one of the more significant things to have occurred in the 80s. Because, well, George was stressing the other day that for feed and bleed, you have a particular time window within which it will work.
Right.
They got to where they were supposed to do it for reasons that Phil can explain better. They didn't immediately do it. They got feed water back before they melted the core, but your quantification of the little remaining dynamics of that decision and how it played out drive the number, and it's not a super small number. I think Brown's Ferry, I looked up Brown's Ferry not long ago, and in the old days they quantified that one at 0.1 conditional probability, and I think think this one comes in on the order of 1%, but not much less.
So I know these analyses are facility specific, and they have to be.
Yeah.
But it'll be interesting to, and like I said, maybe there's something like that already exists, but basically like a benchmarks handbook. You know, like in the reactor physics world, we have the crit safety integral benchmarks studies sponsored by OECD and EA. But wouldn't it be great if we had like a collection of all the near misses that we've talked about?
Oh, we have a database of that in the at the Idaho National Laboratory.
Okay, I'll get with you later.
Okay.